option for this? Let's see.
No, I'm asking Pawan actually.
Oh, okay. Yeah, I think in all of the Zoom talk, it's better to wait for a few more minutes than the actual time.
Manami, maybe you can start.
Okay. So today we have Ursula Whitcher to talk about the counting points on Calabi-Yau variety over finite field. She is from New York, she is generally from US, but she is right now in England, in Cambridge. So it's really nice to have her here, and it's all to you, Ursula.
All right. Thanks so much for inviting me. This is really fun. It's cool to be able to give a talk and have people come from everywhere. I want to talk today about some work that I worked on for a fairly long time with a group of people. So here we are all together. There's Tyler Kelly, who's now at the University of Birmingham here in England. Chuck Duran, who's at Alberta, but this year based at Bard College in New York. Steve Sperber, me, John Voigt at Dartmouth, and then Adriana Salerno, who's usually at Bates, but this year is at the National Science Foundation. So lots of people and lots of travel from all over. The reason this is a big collaboration is because we really did try to pull together knowledge of physics and geometry and mirror symmetry with knowledge of more classical number theoretic information. And so this is a project that really used the efforts of all of the pieces of the team. And I'll try to maybe call out a little bit different parts of the expertise as we go on. Okay. So where can you find this? I think everything I'm going to talk about today has been published. So if you dig into the literature, it is there for you to find. There's two papers. I'm going to concentrate on the results of our first paper in this line of work, which is Zeta Functions of alternate mirror Calabi-Yau families. It came out in IJM. We had a follow-up paper where we looked at some examples in more detail in research in mathematical sciences. And then I have an expository paper if you just want a quicker overview with a little bit more references and so on than what I'm going to talk about today. I've got an expository version of this work in the AMS Contemporary Math series. So our goal here is to use stuff that we know about mirror symmetry to try to prove things about arithmetic. And how are we going to do that? Well, I just want to start by showing you some interesting quartics in P3. This first quartic is very, very classical. It's just the diagonal. You might, depending on your mathematical upbringing, call it the Fermat quartic or the Doric quartic. Then we've got F2L2, which starts out looking like the Fermat quartic. But then instead of having all of the monomials use only one variable, we have an x2 cubed that goes and uses an x3. And then L stands for loop because this loops back around and gives us an x3 cubed and an x2. Then we've got the Klein-Mukai, which again starts out looking like we might be building the Doric quartic, but instead goes into a loop. We could have a pair of loops where we have a two-term loop in two variables and then a two-term loop in two different distinct variables. Or we could have one long loop where we go all the way through all four of our variables. And I'm about to show you some arithmetic information about these quartics, but I need to give you some warnings, and my warnings are going to ramp up in expertise. So first of all, these are not describing isomorphic varieties, say as complex varieties. These are genuinely different quartic hypersurfaces. And then if you are a sort of mirror symmetry expert, you might ask, are these Fourier-Mukai partners? Do they have some kind of derived equivalent, like equivalence of sheaves? And they don't have those sorts of similarities either. They genuinely are distinct in some sense.
They are not biholomorphic in complex analytic sense, right?
Sorry?
So they are not biholomorphic at complex analytic varieties, right?
Right.
But, yeah. Are they birational?
They're not birational. You can relate them to each other using rational maps, but you're not going to get a birationality. It's more complicated than that.
Okay.
So I'm going to just pick a prime and very naively sub in all of the points over the appropriate prime order field and see which of them are solutions to these polynomials. So here I've got my table. It's my table of data for the prime p equals 5. You can see that all of these numbers end in 0. So maybe your first hypothesis would be, oh, it's always a multiple of the prime, but it's more complicated than that. Here's the table for p equals 7. And this time we've got some 64s, we've got some 50s, we've got some 78s. If you're plugged into the sort of numerical intuition on this, you might say, oh, well, 50 plus 64, that's just a difference of 14, and that's 2 times 7. And if I want to get to 78, well, I can add another 14 and get there. So it seems like all of the numbers in this second row of the table are equivalent mod 7, although not equivalent to 0. And indeed, if you keep on, if you go 11 and 13 and so on and so forth, you will observe that we've actually got an equality of mod p for each row and therefore each p in this table. In other words, the point counts don't agree, but they do agree mod the order of the prime that we're counting over. Right. Now, my personal background is geometry, so I think it would be fun to think about families of quartics instead of just a single quartic. And to do that, I'm just going to pick some parameter, I'll call it psi, and add -4 times that psi to the product of all the variables to each of my quartics. And that gives me pencils. And then if I pick an individual family and an individual parameter, I can, again, count the number of points over my favorite field of prime order. For each possible available parameter value, here are the only parameter values that would really make sense are ones between 0 and p. And then again, for a fixed parameter, fiber by fiber, the point counts are going to agree mod the order of the field. So far, what I've been showing you is just sort of experimental information. We literally did plug in some points to count them, but we want to be more sophisticated about that. So our sophistication here, we're going to start by using the zeta function. So you'll recall that the zeta function is a generating function that takes all of the point counts as we take bigger and bigger extensions of the field and throws them all into a single generating function. Now, a bunch of stuff is known about this. This is a really pretty classical number theoretic object. First of all, although we wrote it just as a generating function, it's actually a rational function in this capital T, that's our generating function parameter. And we can factor the zeta function using polynomials that have integer coefficients. And not only can we factor it as the ratio of some polynomials with integer coefficients, we can relate the size of those polynomials to geometric information about our variety. So the product of polynomials that we get is controlled by the dimension of our variety. The lowest and the highest in our indexing of polynomials have very, very nice formats. And then if we're looking at the degrees of the intermediate polynomials, the degrees of the intermediate polynomials are controlled by the Betty numbers of my variety. So somehow, despite being a very arithmetic object, this is pulling in some sort of topological information about how my variety might act, say, over the complex numbers. In particular, if I've got a hypersurface that lives in Pn, I can simplify what's going on with this particular rational function. I can say that in the denominator, it's always going to have a 1 minus t times a 1 minus qt times a 1 minus q squared t, all the way up to that piece coming from the highest dimensional factor. And so the only really unpredictable piece of the zeta function is going to be something that we'll call p sub x, which might be in the numerator and it might be in the denominator, depending on whether the dimension of my hypersurface or equivalently the dimension of the projective surface that I'm embedding it in is even or odd. And we know that everything has rational coefficients here. We can say a little bit more about Calabi-Yau varieties in particular, which are the varieties I'm going to be most interested in today's talk, which is that this interesting polynomial in the zeta function has at most one root that's non-zero mod p. In other words, it has at most one root that's a unit in the p-adic sense. And therefore it is creatively called the unit root. And if you know what your unit root is, you can go back to the fact that your zeta function is a generating function for point counts and use the value of your unit root to determine the value of your point counts mod the order of your field. So, okay. If you wanted to compute a zeta function, well, we know what degrees these polynomials have to have. And we know that it's also given by a generating function. So hypothetically, you could just start computing. You could count over a field, and then you could count over a field of a slightly bigger size and of a slightly bigger size, and keep on going up until you've counted up to about half the sum of the Betty numbers. And then you can use Poincare duality to get the rest of the information. And that would just compute your zeta function for you absolutely, completely. The problem with this as a computational algorithm, if like me, you're interested in higher dimensional varieties, is that the Betty numbers of your variety can get really, really big. And that means that we can have just this huge combinatorial explosion. And so although hypothetically, given world enough time and a fast enough computer, we could just grind through and get the zeta function, in practice, it's much, much harder to actually figure out what it should be. So in terms of like people who have written down or implemented code that you can use to compute zeta functions for higher dimensional varieties, to the best of my knowledge, the state of the art is still work of Edgar Costa. Edgar Costa's code, we can do K3 surfaces in projective free space. We can do K3 surfaces realized as double covers of P2. We can do a handful of very special three-folds or very special four-folds. And that's kind of it. We don't have a lot of interesting models where we can really compute this stuff. On the other hand, the examples that I showed you were K3 surfaces in P3. So we can use Edgar Costa's code for specific primes and try to get the zeta function for these examples that we care about. So for instance, here's the Fermat. And if we count the Fermat, if we compute the zeta function for the Fermat here when p equals 41, we get the interesting piece of our zeta function. Well, it has a 1 minus 41t to the 18th. That's not so interesting. And then there's a special degree 3 term. Similarly, if I looked at the Klein-Mukai, which has the x naught to the 4th, and then this loop of variables, I would get some other stuff at the beginning and some other stuff at the end, but I still get the same exact degree 3 term. There's this degree 3 term in the zeta function that is preserved between these two families. And in fact, if you went and you took those other examples that I showed you in the tables at the beginning of the talk, and you compute those zeta functions for the same prime, you'll see again that there's this repeated piece of the zeta function. So our goal when we set out is to see if we could really identify this repeated piece of the zeta function and explain where to find it and how it was coming from in more generality. So how do you actually do this? You need to understand the characteristic polynomial, the Frobenius action, on your favorite p-adic cohomology space. The technical details are going to differ depending on exactly which p-adic cohomology you use. Edgar Costa's computations use Monsky-Washington cohomology. In our work, we have Steve Sperber, who is really one of the world's experts on working with Dort cohomology. So we use Dort cohomology to work out our arguments. So what does this have to do with mirror symmetry? This is going back to work of Philip and Xenia and Fernando Rodriguez-Villegas. And Xenia's in the audience, so feel free to speak up and correct me if you want to say a little bit more about how this story came to be in the beginning.
Okay, you're saying it well. Yeah. Perhaps later, I mean, as I said, I have to leave today, but later we can talk more about all the work that has been going on in computing zeta functions.
Yeah, that sounds fun.
Yeah, there is quite a bit of activity that perhaps you might want to know about. But perhaps we can meet some more, or Philip is in the audience too. If he can stay later, perhaps he can tell you about it. I mean, there is quite a bit of coding going around on zeta functions that are beyond the example that you mentioned.
Awesome.
Yes,
So
indeed, but these are mostly in the physics literature, in fact, and they're all mixed up with black holes and things of that sort. So it's not. Anyway, so there's something that we can talk about later. I mean, if you like, or you can talk with Philip if I have to leave. Yeah.
Yeah, that sounds really exciting.
Okay.
All right. So we look forward to the black hole zeta functions, but for now, let me just remind you, if you look at the Hodge diamond for now, we're thinking of quintic hypersurfaces in P4 and their mirrors. For quintics in projective space, well, there's not a whole lot going on except for in their middle cohomology, where we have 101 different ways that we might try to deform our holomorphic form. But then a mirror quintic turns this Hodge diamond on its side, as it were, or you can think of it as actually reflecting the Hodge diamond through a diagonal line. And we have the ones turn into 101s and so on and so forth. So the mirror quintic doesn't have a lot going on in the middle cohomology, but then it has lots of extra actually algebraic classes that we can see in this 101 here. Well, if you think about how would a Calabi-Yau threefold in its mirror, like how would their zeta functions be related? we know that there would be some kind of relationship between the zeta functions, just because the Hodge numbers are interchanged, and you can get the Betty numbers by summing along a row of Hodge numbers. And so we know that the degrees of the polynomials of the zeta functions between a threefold and its mirror would have to have some kind of predictable relationship, just because we've flipped the Hodge diamond. But in fact, it has been shown by Philip and Xenia and Fernando that for the Fermat quintic and the green Plesser mirror, you can get a lot better. You actually have a common factor in the zeta function between the Fermat quintic and the mirror quintic. So just to remind you what the green Plesser mirror is, if you, and let me also go down a dimension. So let's go back to quartics instead of quintics. We're going to start with all of the smooth quartics in P3. We're going to look at the Fermat tensor. So the same kind of Fermat with a deformation that we were thinking about a little while ago. This admits an action by z mod 4z squared. So the idea is we notice that we can multiply any of the coordinates by a fourth root of unity without changing those beginning monomials. But then if we want to fix an individual variety in this pencil, we should also make sure that that final deforming monomial minus 4 times xyz w is also fixed. And that places one constraint on our fourth roots of unity that we can multiply by. And we have a second constraint because we're working in projective space. And if we multiplied every coordinate by the same fourth root of unity, that wouldn't do anything. So if we mod out by that group action and resolve our singularities, that will give us what is now the mirror quartic. Okay. So you get the mirror family to smooth quartics in P3. And again, smooth quartics in P3 would have lots of ways that we could deform them in a complex geometry sense. The mirror really is a one parameter family in a natural way. So if you look at the Fermat quartic and you try to work out what the interesting bit of its zeta function should look like, then it breaks down into essentially three parts. There's this degree three thing that I showed you in Edgar Costa's example earlier. Well, in the example done using Edgar's code earlier. So this is the same sort of R, our interesting degree 3 R we had before. And then depending on the exact psi, we could have some pluses or minuses in these other parts. And we've also got a piece that depends on whether P is 3 or 1 mod 4. And if you look at what is the zeta function of the mirror, well, on the mirror side, we still have the R sub psi. This degree 3 polynomial is preserved. And the rest is just going to factor all the way down to the 1 minus pt to the 19th. Morally, that's because we have a ton of algebraic classes now, and every single one of those algebraic classes that we created by modding out by the group and resolving is giving us a 1 minus pt factor here. Okay. So this factor R sub psi, it looks like you can relate it to periods of the holomorphic form on this variety and its derivatives, and it's preserved by mirror symmetry. So a big question is, this is an amazing example. We've seen something like this for quartics and something like this for quintics. And you might ask, how can you generalize this to other situations? So one person who thought about this was Daxing Wan. He showed that it works for the Fermat pencil in any dimension and for the green Plesser mirror, at least in the sense that the unit roots match. And so you'll have this kind of congruence counting over the order of the field in terms of point counts. Shabnam Kadir in her dissertation worked out a 2-parameter example related to optics in a weighted projective hypersurface and its mirror. And she showed that in the octic example, you get a common factor, and then argued that the same kind of computation should show that in general, if you were looking at torically realized Fermat hypersurfaces, you should again get a common factor in the zeta functions. Adriana Salerno and I have thought a little bit about what you can see for the Batarev mirror symmetry construction, or alternatively for looking at hypersurfaces and Gorenstein-Fano weighted projective spaces. Our arithmetic techniques there are maybe not as powerful, at least in the work we've done so far, but we are able to say some things about these kinds of unit root style or congruent style computations. But what I want to really dive into today is I want to look at trying to generalize the story for the mirror quintics and mirror quartics to Berglund-Hupsch-Kravitz duality, BHK duality. So here we have Berglund and Hupsch and Kravitz. Berglund and Hupsch are physicists. Mark Kravitz did his PhD at University of Michigan and then went into finance, which is why this is a very finance-y photo when I went looking for him on LinkedIn. All right, so what are we gonna do? We're gonna write down a polynomial. We want it to be n+1 monomials and n+1 variables. And we're going to think of our polynomial as being given by some kind of matrix of integers that tells us what is the power that we raise each variable to. So here, the rows correspond to a monomial in our polynomial, and then the columns would pick out an individual variable. Okay, and we want to put some conditions on this polynomial. We say it's invertible if, first of all, this matrix A is an invertible matrix. That's just like a requirement, right? If I'm going to call something an invertible polynomial and it comes from a matrix, my matrix better be invertible. And then there are a couple more technical conditions, which are essentially here to give us nice geometric behavior. I want to be able to have weights so that if I fix a particular column and I do a weighted sum over that column, I always get the same constant. And I want to make sure my polynomial only has a critical point at the origin where all the variables are 0. And then there's a condition called the Calabi-Yau condition. We say that an invertible polynomial satisfies the Calabi-Yau condition if this D that we define using the weights is actually just the sum of all the Q sub J's. So what do those technical conditions do geometrically? Well, first of all, the weights give us a weighted projective space for our polynomial to live in. So if we take constant weights 1, we're just going to be looking at a polynomial in regular projective space, like the examples that we did at the beginning. And then the Calabi-Yau condition is to force us to get a Calabi-Yau hypersurface in this weighted projective space. In other words, if the sum of all of the degrees is the same as the sum of the weights, we're going to get a nice Calabi-Yau hypersurface here. So having defined invertible polynomials, you might want to know how many of them there are. And this is worked out pretty early on by Maximilian and Kreutzer and Gerhard Skarke. So this is Kreutzer in the nice jumper, and this is Skarke looking a little impatient with this particular picture, but I'm glad now that we have it. So they proved that if you've got any invertible polynomial up to overall symmetries, you can write it as a sum of invertible potentials of really nice types. You can have Fermat types where you have just a pure power. You can have a loop type where you have x1 raised to some power times x2, and you go on in that pattern for a while, but then you finally loop back and have something times x1 again. Or you could have a chain which starts off looking like you're going to make a loop, But instead of looping back again, you take your final variable and you raise it to some power on its own. So notice that that's different from just adding on a Fermat because there's a match between the variables used in the final two terms. I think Kreutzer and Skarka might actually have called chains tadpoles, and I'm a little sad to have lost the tadpoles from the literature, but sometimes these things happen. Okay, so if we wanted, we could fix some weights in some dimension and write down all of the invariable polynomials. We can also write down a group action on our polynomials. And the way we compute the group action feels a lot like the way we computed the group action on the Fermat pencil when we were doing the green plus or mirror. We're going to look at the diagonal symmetries of our polynomial, which are just going to involve some powers of roots of unity. And we're going to mod out by the ones that have the same action diagonally on every single variable. And that will give us some kind of group action that acts non-trivially on our variety, and it fixes the holomorphic form on our Calabi-Yau. Okay, so given this machinery, we're ready to define a mirror. We're going to start with some in matrix A, building some invertible pencil that defines a Calabi-Yau X sub A. Then we're going to just transpose our matrix. If we transpose our matrix, we can get a new polynomial because now we're going to be reading across new rows that used to be columns to determine each monomial in our polynomial. We define a new group, which is the group that we get by running the same computation of symmetries now on the transposed polynomial side. And so our mirror is going to be an orbifold, a quotient of our transpose polynomial variety modded out by this group. And you can soup this up in general. The way I just wrote it down, on one side, we had just a polynomial that, just an invertible polynomial and a Calabi-Yau, which you could think of as taking your invertible polynomial and the trivial group. And then on the other side, we got a new Calabi-Yau and a group to quotient by. If you want, you can take different subgroups on either side, and the BHK mirror in general gives you a way to match across so that if you take an appropriate subgroup acting on one side, you can get the appropriate mirror on the other side. But all we're really going to need in terms of the results today that I want to talk about are the matrix and its transpose and the fact that we get an orbifold quotient that is the mirror. So here's the question that drove us to look into the arithmetic of this particular set of families, which is if we know that the transposed matrices have common properties, which would say, in other words, if we know that the mirrors, the BHK mirrors of our varieties have common properties, can we use that relationship between the mirrors to make observations about the varieties that we started with? And let me just add, I've been telling you about BHK for individual Calabi-Yaus, but we can also do it for pencils in just the same way that we were defining pencils earlier. The arithmetic works out a little bit more nicely if we, instead of taking our constant to be the number of variables involved, we take our constant to be the sum of the dual weights. Here's our theorem. Let's suppose that we've got invertible pencils of Calabi-Yaus in P sub n and P to the n. And let's suppose that the dual weights are the same. In other words, I'm going to take A transpose, I'm going to take B transpose. I'm going to calculate the weights of those transpose matrices. And I'm assuming that the weights on those transpose matrices are the same list of numbers, or equivalently, that my mirrors of my invertible pencils live in the same weighted projective space. Then for every psi satisfying a divisibility condition on my sum of the dual weights, and assuming that I meet a smoothness condition, so it makes sense to be talking about smooth Calabi-Yaos in this particular field, then my polynomials are going to have a common factor. And that common factor isn't a trivial common factor. We can compute its minimum size, and its minimum size is just some function that depends on the dual weights. We can also give you a maximum size, like what's the biggest that this preserved factor can be. And that maximum size is related to the way that our group of symmetries acts on the appropriate cohomology. So here's an example, just going back to the set of examples that we started with. In this case, their mirrors are also quotients of things that live in regular projective space. And the degree of the piece of the zeta function that's fixed, that interesting piece, is indeed degree 3. There's another way to look at this story that we're telling, which is to notice that in this family, for any of these varieties, if we take our field that we're counting over to have enough roots of unity in it, then the zeta function is going to end up having a really particularly nice form. It's going to look like just 1 minus t times 1 minus qt to the 19th times the 1 minus q squared t times this fixed piece r. So our zeta functions aren't equal. We've already seen that they're not equal for arbitrary primes. But if we somehow let ourselves have a nice enough field, then the zeta functions will become equal. And we shorthand that by saying they're potentially equal. So another way to say this is that if we look back at the family of miracortics, then for any of these pencils that we've been looking at, our friendly set of examples, the zeta function of any choice of pencil from that list and of the miracortic are potentially equal, no matter which of those 5 families you pick to start with. So here's a different example, just to show you the sort of different possibilities that you can get. You might have noticed that our first examples were all Fermat and loops. They didn't have any chains in them. Here are some invertible pencils where we do have some actual chains and the corresponding symmetry groups. In this case, we actually get a bigger preserved piece of the zeta function. The degree of our preserved piece of the zeta function is actually degree 6, not just degree 3. And this is the complete story as far as invertible pencils in P3. If we're looking for ways to match common factors in the zeta function, you can write down other invertible K3 pencils in P3, but they have dual weights that don't match with anything else. So this is the complete story as far as when can this theorem help you group invertible pencils of K3 surfaces in projective 3 space and find common factors of their zeta functions. Another way that you could try to dig more information about this theorem is you could look in higher dimensions and maybe restrict information about the dual weights somehow. So we can specifically say in PN, if the common dual weights are just 1, 1, 1, and 1, in other words, if the mirror of our Calabi-Yau is a quotient of something living in regular projective space, then the common factor is just going to have degree n. So that tells us that if we take any two invertible families that look like some Fermat and some loop, where j plus k equals n, so we're building them in the right dimension, we're going to have a common factor of exactly degree n. So that's really nice. That lets us make predictions about the structure of zeta functions going up into very, very high dimensions, where it might otherwise be difficult to try to extract information directly. So I'd like to talk a little bit about some of the more technical work that goes into proving this stuff, but does anyone have questions before I dive into that? All right. So what's really making this argument possible is the observation that if we have a piece of p-adic cohomology that is stable under the Frobenius action, we're going to have a factor of the zeta function. That does depend a little bit on the prime p that you're using. And that's one of the reasons that we do have to think a little bit about divisibility conditions in terms of what predictions we're going to make. But we also need some complex geometry information, which is we need to know what is the differential equation that's satisfied by the period of the holomorphic form on our variety. We have a unique holomorphic form up to scalings because we're working with Calabi-Yaus. And by a result in Swanchegar's thesis, the Picard-Fuchs differential equation that we get only depends on the dual weights. Then we can take that essentially complex analytic observation and move it over to an observation about p-adic forms and Dorf's p-adic framework. And that means that looking at the objects that you determine while you're computing the Picard-Fuchs equation, we're actually going to get a subspace of the p-adic Dort cohomology that's stable under the action of Frobenius. So that gives us our lower bound on our preserved degree in our theorem. And this subspace is also fixed by the overall symmetry group action. So that gives us our upper bound. Let me show you a little bit more of the nitty gritty with the hypergeometric differential equations that you get. If we look at this a little harder, this also gives us a way to identify what the function was of the dual weights that told us what the size of our common factor was going to be. So hypergeometric equations tend to involve lots of little fractions. We're going to take fractions, d to the t here is just the sum of all our dual weights. So we're going to take 1 over d to the t and then 2 over the sum of our dual weights all the way up until we've got sum of our dual weights minus 1 over the sum of our dual weights. And then we're going to take a bunch of maybe shorter lists of fractions where we're taking fractions dividing by the individual dual weights instead of the sum of all of them.
When was this thesis?
I'm not sure exactly. It's not, I want to say sometime between 2000 and 2010, somewhere in there.
Okay, okay. Okay, go ahead.
I've got a copy of it if you find yourself wanting to read it. So let's make some multi-set.
Actually, sorry,
Yeah.
can I ask a question? Is this, could you go back a slide? So Cigar showed that the Picard-Fuchs equation is a hypergeometric differential equation. For what cases is this?
So this is, the cases that we're looking at are for these invertible pencils
Oh, I see.
in projective space.
I see.
Yeah, I'm trying to remember whether she looks at invertible pencils that are also in weighted projective spaces, and I don't remember off the top of my head whether she does or not.
Okay. So this is of course not. I just want to know yeah. So which classes of Calabi-Yau this covers? Because of course there are examples in which the Picard-Fuchs equation is not hypergeometric, right? But
right, of course, yeah. This is really specific to the invertible pencils.
Yeah. Okay. Yeah. Thank you.
Okay. So we're gonna make multi-sets. That just means we might have some repetitions, like it could be that our betas are the same from time to time. And so we're gonna throw all our alphas and our betas into a list, maybe with some repeats. And then it could also be that our alphas and our betas that we've made in this way have an overlap. So we name our overlap capital I. Let's define a differential operator. That's just our parameter times the derivative by that parameter. So here's a theorem of Gar's if we want to make it a little bit more specific. Let's suppose we've got an invertible pencil of Calabi-Yau and -1 folds, say now in Pn, determined by an integer matrix. And let's suppose that the matrix has dual weights Q0 through Qn. Then the order of the Picard-Fuchs equation is just going to be the sum of the dual weights minus the size of whatever that intersection was between our alpha list and our beta list. And you can write down the Picard-Fuchs equation really explicitly, and it's actually really pretty. It's this specific kind of hypergeometric differential equation that has this form with the alphas and the betas in it. So let me quickly remind you what a hypergeometric function would be. I just showed you a hypergeometric differential equation. A hypergeometric function would have a similar kind of deal with alphas and betas. And we have, with a ratio of what look like pieces of factorials with alphas and the betas, like alpha times alpha plus 1 all the way up to alpha plus something, divided by something similar with the betas, and then we divide by k factorial, and we multiply by our variable to the kth power. So one way to think of this Picard-Fuchs equation is that it is the differential equation that has a solution given by a hypergeometric function of this form. So again, that's pretty nice. We can compute this out relatively explicitly after spending a little bit of time staring at dual weights. So, and we can use this to tell us something about the unit root. So let's suppose we've got invertible polynomials and n+1 variables that satisfy the Calabi-Yau. We are assuming here that our starting polynomials live in Pn. Let's suppose that our transpose matrices have the same dual weights, have the same weights, or that, in other words, that we have the same dual weights. Then for any parameter that we want, and in all characteristics, so without imposing the divisibility characteristics we had in our main theorem, the unit roots match, or neither variety has a non-trivial unit root. In other words, if you start looking at the roots of your polynomials, there's nothing that's a p-adic unit other than, 1. So in that case, the supersingular locus would be the same for both pencils. Again, we have a matching result about unit roots, which doesn't care about these more technical conditions. In fact, it doesn't even care about smoothness. And we can rephrase that in terms of a congruence on point counts. So for any parameter in our family, even if it happens to be a parameter where for this particular psi and this particular finite field, we lose smoothness, we still have an equivalence of point counts mod the order of the field. The reason that this works is that we can write down a formal power series using those same hypergeometric parameters, but now using information about hypergeometric functions over finite fields instead of arbitrary hypergeometric functions. And then that proposition would follow from results of Miotani in the smooth case and keeping our parameter away from 0, or from results of Adelson and Sperber if you are trying to get everything that I've just claimed to you, including the non-smooth case. And again, these are the same parameters as the Picard-Fuchs equation. So we've got what felt like a very complex analytic computation, which is still having ramifications working on hypergeometric functions defined over finite fields. If you just care about the common factor part, there is another way to prove the result that I showed you about the common factor of the zeta function. And that is to use a covering function, to use a covering map that will map from some sort of overlying variety down to each of the pencils that we saw. And you can use that covering map to extract this result about the zeta function and some other geometric information about what's going on in the family. That's work that was done by Remke Klusterman after we published our first preprint. And then something that we went on to think about is, okay, we described very carefully what happens to the piece of middle cohomology corresponding to the holomorphic form and its derivatives, and we had that Picard-Fuchs equation, and it was hypergeometric, and that gave us a factor of our zeta function that was preserved through all of our families. But what if we wanted to describe the pieces of the zeta function that aren't preserved? What if we wanted to just say what happens in the zeta function as a whole in each of these families of quartics? So it turns out that you can also match these to periods and to differential equations satisfied now not by holomorphic forms. And we were able to do that in full detail for F4, for F2L2, for F1L3, for L2L2, for L4. If you go up a dimension, you'll see this already in the work of Xenia and Philip and Fernando for the quintic. So you can work things out and decompose them in a very pretty way. It is tough and meticulous work to do. And let me tell you about the computation for our families that we started with as our example families. There is a canonical way to break down the point count over a finite field. The summands are either going to be trivial or they're going to be hypergeometric in the sense of hypergeometric counts over finite fields. When you have good divisibility conditions, then there is, for each of the pieces of this decomposition, a corresponding hypergeometric Picard-Fuchs differential equation, and we can match this canonical summand to that hypergeometric Picard-Fuchs differential equation, and also to a hypergeometric function defined over a finite field with the same parameters. So let me show you what it looks like. Here we've got F4, which had already been done, but we worked it out again just to make sure that our techniques were consistent. So in each case, we've got a list of alphas, we've got a list of betas, and then we've got the multiplicity of the corresponding factor. Because we've got this preserved piece of order 3, we're going to see that at the top of each piece of the table. And then you can see that the other parts have different orders and combine in different ways, depending on exactly which of these families you're looking at. And we're going to have slightly different restrictions on the field as well. Again, depending on exactly what's going on with a specific family, or really with the specific parameters of the hypergeometric functions, because not all, some of these are harder to define over finite fields than others, depending on the exact parameters. We also need the divisibility conditions to ensure that our action of Frobenius is actually compatible with the action of this group. But we can write down, when we have that, information about the complete factorization of the family. So here it is again, in all of its glorious detail. And we can say a little bit of information about where do these factors actually arise. Sometimes in order to see the factorization in the zeta function that seems natural from the point of view of the group acting on the space, we have to extend the field that we're working over a little bit. And so the final column of this table is telling you a bit more about what's going on there and what is the sort of most natural field in order to factor the interesting piece of the zeta function for each of these families. So that's lots of information. To sum up, we've given you a machine that can take in information about invertible pencils and uses intuition from their BHK mirrors to tell you stuff that's preserved in their zeta function. And then we've also glanced a little bit at some technology that would use similar intuition about hypergeometric functions over finite fields and hypergeometric differential equations and get much more detailed and fine-grained information about the complete zeta function of a variety. And let me stop there and see if there are any questions.
Let's thank our speaker. Is there any question for Ursula? If not, I wanted to ask, so how did you figure out which degrees are interesting? For example, for F4, you have these 3 examples. Is it just because they're interesting, or these are all the examples you're considering?
This is actually a degree that works like psi by psi. So we're looking at, so our interesting piece of our polynomial, it should always end up to 21, just because for geometric reasons we have like, that's how big that piece of the zeta function is going to be that we don't know about. So we're asking how do I break down this degree 21 polynomial? There's this degree 3 piece that's standard. And then the other pieces, it's going to depend on how the symmetry group is acting. So in F4, we had Z mod 4Z squared symmetry group. and that will break up the cohomology space into blocks. And then we'll use the information about those blocks in the cohomology space. We expect to see the degrees of the blocks and the degrees of the polynomial factors to match. And they more or less do. There's a little bit of subtlety because sometimes you can have like what you expected to be one block, but it might have a factoring further or some kind of combination or something like that.
I see.
Yeah.
And also
But yeah,
you mentioned, oh, sorry, go ahead, Ursula.
No, go ahead.
So also you mentioned that, for some specific prime, this, when you are saying potentially equal, right? But you mentioned that for some specific prime, you can actually get the equality of the zeta function. So did you like check some examples of, which primes are giving you this equality for, for example, for all these pencils you have in this example, do you have, like, did you compute examples of which primes are nice and give you equality?
Yeah, so what we really need is we need to have enough roots of unity. And I would have to double check it, like exactly what those predictions are. But you can like sit down example by example and be like, okay, which roots of unity do I actually need? And be very precise about like, these are the roots of unity that I would need in my field to get the factorization all the way.
Oh, I see. So it might not be just adjoining one single roots of unity. You might have to adjoin multiple roots of unity to get to that field. Nice.
Yeah.
Nice field. Okay. Okay. Thank you.
Yeah, there's also a geometric intuition, which is that the really nice factor that just like 1 minus q times capital T should correspond to an algebraic class. So you're sort of asking like, what is the field where I can see that this class is algebraic, like over that field?
I see. And also in the table, you have these dashes for alpha and beta. Is it the anything works, or you cannot find alpha, beta?
It's that these are things that are trivial factors, so they're not hypergeometric because they're just like more boring than that.
Oh, I see. Okay.
Like they end up looking like, sums of, q plus q squared or something like that.
I see. Okay. Okay. This is really interesting. Are there more questions for Ursula?
I don't have a question as such. I just wanted to make a comment. So
yes.
Thank you, Ursula. That was a very interesting talk. There are really lots of rather interesting and intriguing examples in your tables. I wanted to point out that it's possible, of course, to compute these zeta functions working from the Picard-Fuchs equation. So you can work from the periods, and in particular, Duco, so AESZ. So the S is Van Straten, and the others, I don't remember all of them, but A, E, S, and Z have a list of 500 Picard-Fuchs operators corresponding to one-parameter families of Calabi-Yau manifolds, and working from the Picard-Fuchs equations, it's possible as a practical matter to calculate the zeta function. So that gives a host of examples if one wants to look at this. Okay, so that was my comment. Okay.
Or at least one piece of the zeta function, right?
Well, okay, so those are one parameter. Those are one parameter models, or one parameter differential equations. Presumably one could extend this for a Picard-Fuchs system if there's more than one parameter. but still, it would be good actually to discuss what the intersection of that work is with this work, because there again the interest is in seeing when the numerators, in that case the numerators of the zeta function, factorize.
Mhm.
So you have something which is generically aquatic, but a piece that's generically aquatic, but it will factorize in various ways. And it's interesting to see when that happens. So it will occasionally factorize, right, for special values of the parameter or special primes. Or...
Right, yeah. And sometimes it has to factorize just for sort of very boring reasons, like, you know, if you have a degree 3 thing, then it's maybe forced to have a linear factor, and et cetera, et cetera. But yeah, there could be more interesting geometric reasons too.
Yes, so when there's a conifold, for example, when your parameter corresponds to a conifold singularity, then this degree 4 thing will factorize into a linear piece and a degree 2 piece.
Mm-hmm.
And there are other interesting things, which is what Xenia was alluding to. Sometimes we'll factor into 2 quadrics. And that seems to be to do with interesting cases such that where you have in the string theory, your 10 dimensions is a Calabi-Yau manifold. 6 of the dimensions are a Calabi-Yau manifold corresponding to a special value of the parameter, and the 4 dimensions correspond to a black hole, an extremal black hole, and the total configuration is only non-singular for the special values of the parameter. And then the interesting thing is that the special values of the parameter have then have interesting number theoretic properties. And one of the ways you see this is that the quartic polynomial factorizes into 2 quadrics.
Mm-hmm.
But there are other factorizations, again, some which are understood, some of which are not so understood. So it would be nice to understand what the analog of that is in these examples also.
Yeah, that is interesting. Thank you.
Are there more questions or comments for Ursula? Well, if not, let's thank Ursula for this amazing talk.
Thank you, everyone, for coming.
Thanks, Manami, for sharing this talk also. Thanks, Ursula.
Yes.
Wonderful talk.
Yeah, it was really nice.
Thanks.
Okay.
Okay. Owen, you can stop recording and stop the live stream.
Okay.
Okay, Ursula, see you.
Bye.
Bye.
Bye. See you later.
See you.